Right, so hi, I'm Durrant, so I work for Citrix. I'm based in Cambridge, UK. I've been a contributor to the Xen project for many years now. I'm community lead for Windows PV drivers, but I also work on the hypervisor, QEMU and Linux CompSci. And today I'm going to talk about something that George mentioned earlier about reducing the attack surface on QEMU. So first of all, I'd like to acknowledge the work done by Ian Jackson, George Dumap and Anthony Farad on this and the help they gave me with preparing this presentation. So just a bit of background first for those who don't know, there's kind of a couple of different ways we use QEMU with Xen. First of those is to supply Paravirtual backend for front ends in our guests. So there's actually Paravirtual backends for various protocols in QEMU, network storage, frame buffer, keyboard and mouse, etc. So that's one of the roles that QEMU plays. In this mode, it behaves roughly the same way as a kernel backend. So I've called the domain here a service domain. It's typically DOM0, but it doesn't need to be. It maps the shared rings in the same way that kernel backends do, and guest IO requests appear on those rings. Communications done via event channels. Xen provides all the necessary libraries to do this. And in this mode, the service domain does not necessarily have to have privilege over the guest domain, because it doesn't need to map the guest memory directly. Everything's done through the grant event interfaces. So that service domain has relatively limited privilege over the guest, but it still needs to make hypercalls. So there is a way, if the guest was able to compromise that service domain, that it could then use that to attack Xen by the hypercall interface. But I'm going to focus on QEMU's other role, which is as an emulator. So in this picture I've shown it running as an emulator. Essentially the emulator could be a stub domain, but typically QEMU is running in domain 0, so it is running in a fully privileged domain. The main reason for not using stub domains is scalability, and this is why we don't use them in XenServer. Because if you had a stub domain for every single guest domain, that would be a lot of domains running on the system. It would limit our ability to scale. So in this mode, Xen traps I/O and forwards it to QEMU via the XenServer interface. QEMU then handles those I/O requests. If the data is not immediate though, then it has to map the guest memory to get that data, and also potentially has to map guest memory to emulate the EMA as well. So in this mode, the emulator domain must have privilege over the guest domain. And also, like in the service domain case, QEMU makes hypercalls. So let's have a look at our first attack vector. So the first attack I'll focus on is that shared memory interface that it uses to handle IO emulation. When QEMU starts up, it needs to get Xen to set up shared pages that are going to be used to drive the IOREQ protocol, which is the way that the way that Xen passes the information about trapped IO to QEMU. And I'll just mention there are a couple of pages that are used to doing this. The synchronous page contains an IOREQ structure, which is the way in which Xen describes an IO. And it contains, the sync page contains one of those per guest CPU, and that's used for handling synchronous I/O. There's also a second page, which is used for handling deferred or buffered I/O. And that's typically, well, in fact, it's only used at the moment for handling memory writes through the VGA aperture, where we know that those memory writes don't have side effects, even though they're essentially MMIO. So we pass them lazily to the emulator. So, having set up the frames, they have to be mapped by both Xen and QEMU, because it is the shared protocol, shared memory protocol, so they have to be mapped in both places. And that's typically done by QEMU using a foreign memory map operation on the guest, because the frames are part of guest memory. So now the protocol can start operation. So IOREQs are passed by Xen up to QEMU, handled by QEMU there, the emulation has completed the information to pass back to Xen, and that's fed back to the guest. but those pages are still visible in guest memory space. Now, they're in the A20 reserved region, but there's nothing to stop the guest from mapping those pages. They're actually at well-known frame numbers, and that could start, and the guest could then start to mess with the protocol that's going on between Xen and QEMU, which is obviously not a good thing to do. So the mitigation against this particular attack vector is part of the IOREQ server API that we added in Xen, which is the enable call. When the IOREQ server is created in Xen, actually the protocol is not immediately operational. When those shared pages are mapped by QEMU, Xen will not actually forward I/O by default. So actually, when the pages are still visible to the guest, there's nothing you can do to actually mess with the protocol in operation. So when the enable call is made to actually start forwarding I/O from Xen to the QEMU, we actually remove those pages from the guest P2M. So that prevents the guest from actually mapping those pages and messing with the protocol. But it comes with a couple of complications. And the main problem with this is that when you migrate a guest from one host to another host, you need to put those pages back in. Otherwise, they don't get migrated to the far end. And then when you start the emulator on the far end, there's no pages to use, and the protocol, there's nothing to, the protocol basically can't work because there's no memory for it to back it up, and basically you get a migration failure. So yeah, it's complex to drive. So it would be much better if those pages never existed in guest space at all. So that's the next part, which is Hypercall I added to Xen recently. This is in 4.11. It's called Xen acquire resource, and that provides a way of mapping memory-based resources that are assigned to a guest for it, essentially to do with guest operation, but mapping them directly from Xen without them ever having to be in guest memory space. So now, when you set up an IOREQ server, the pages are not allocated in guest memory. The sync and buffer pages are allocated directly by Xen, and you use the new hypercall to now map those into QEMU's memory space. So let's have a take a closer look at the hypercall itself. That's the structure. First thing you'll notice it contains is the DOM ID of the guest whose resource it's mapping. The next is type, in this case type IOREQ server. That's actually the only one that exists at the moment. Then there's the type of page, so there's that synchronous I/O page or there's the buffered I/O page. So there's always one buffered I/O page, but for reasons of needing to expand the number of vCPUs a guest might want, we have allowed more than one synchronous IOREQ page. As I said, that synchronous page contains an IOREQ structure per guest CPU, and actually in a single page you can only get 128 of those. So at the moment we're limited to 128 vCPUs in guest because of that. However, in future, if we want more than one page, we can obviously extend the number of CPUs in the guest, and this interface allows for that expansion. The next thing of interest is the frame list itself. Now, if your tools domain is PV, or if your tools domain is APM, this actually plays two different roles. If your tools domain is PV, then you make the hypercall, and Xen will fill in that list with a set of NFMs which you then map into your PV tools domain. However, if your tools domain is HVM, then what you need to do is you need to nominate a set of guest frame numbers, you pass those in, and Xen will then fill in those frame numbers in your P2M with the appropriate pages that you can then map. So, this is all hidden behind a new IOPTL and priv command, and there's a library based upon this now. So if you go look in Xen foreign mem in 4.11, there's a new map resource operation, and while I said that IOPTL is currently queued for upstream, I believe that's now actually been committed. I think it's in 4.18, I'm not sure. But yeah, I think it went in a few weeks ago. So this should all be workable now if you get the latest 4.11 RC, and you should be able to use this. So next attack vector is hypercall memory handles. Now, in all these further attack vectors that I'll talk about, we're going to assume that QEMU's already been compromised. So something's mounted a successful attack by one of the device models. Device models are complex things. They have been buggy. I think the most recent vulnerabilities have mainly been in the graphics device models. So we'll assume that QEMU has been compromised using one of these attacks, and then we'll look at how we're going to limit what it can do and the damage it can do. So memory handles are the first one. We'll look. Yeah, so the hypercalls that QEMU makes are typically issued by the privcommand driver, which is the kernel driver in Linux. And we'll assume that QEMU has already been compromised. Now, the compromised QEMU causes, basically talks to the privcommand and tries to cause it to issue a hypercall. Privcommand then issues the hypercall to Xen. But the interface in privcommand that's used to issue hypercalls, you can use to issue any arbitrary hypercall you like. So basically, QEMU can just go and do anything it wants to Xen, to try and attack Xen. So if we look at the one particular hypercall, this is called the track dirty VRAM hypercall. This is used for, this is typically used by QEMU to track updates to the guest frame buffer, so it knows exactly which areas of the screen have changed, so then it doesn't have to scrape the whole of the VRAM to update the VNC frame buffer. But one of the things that this hypercall contains is a pointer to a dirty bitmap, and that's in QEMU's memory space. And there's nothing to, there's no auditing essentially on that hypercall. So that dirty bitmap could be filled in with any value you like. It's a QEMU controlled value. Now typically, as I said, it points into the emulator domain's own memory, but there's no auditing, and Xen will blindly write the dirty bitmap to whatever that is pointing at. So QEMU could fill that in with a DOM0 kernel address if it liked, and Xen will then happily write the dirty bitmap into DOM0 kernel memory. And given that QEMU controls the actual frame buffer in the guest as well, then it can essentially cause an arbitrary bit pattern to be written into DOM0 kernel memory. So now you essentially have arbitrary write access into DOM0 kernel memory using your compromised QEMU. So what are we going to do to stop that? Well, the mitigation for this one is a new hypercall that was added in 4.10, I think it was originally integrated in. And this is basically the way in which we limit what hypercalls QEMU can make. So we'll start broadly with the same picture before. We have QEMU there. We have the library which is used to issue the DMOP hypercalls, and we have privcommand. So let's assume that QEMU has been compromised, but let's assume for some bizarre reason that it's going to be a good citizen and use the appropriate library to issue hypercalls. And we'll come back to why that is relevant in a few slides' time. Now, instead of issuing an arbitrary hypercall, it's going to use the DMOP interface, and the DMOP interface is then going to issue the hypervisor DMOP hypercall to Xen. Now, the crucial thing about this hypercall is all the memory handles that pass via this hypercall can be audited, and the reason for this is the structure of the hypercall. And the hypercall basically looks like, well, this is the arbital rather than the hypercall, but it looks like this. So that the arbital specifies the domain which you're operating on, and then it just specifies an array of buffers, and the buffers are just pointer and extent values, which can be audited by privcommand using the access OK kernel primitive, just to check that those memory ranges are actually legitimate. And then this is mechanically translated by privcommand into the DMOP hypercall. As you can see, it's basically got the same structure: DOM ID, number of buffers, buffer structures, each buffer is a guest handle and a size. And that means that you can't, as a compromised emulator, get the privcommand driver to point to pass an arbitrary memory handle into Xen. So it gives us some degree of safety. So we'll look at the next attack vector, which is the hypercall target domain. As George mentioned earlier, QEMU essentially could read the memory of any arbitrary guest because it's running in DOM0. So what are we going to do to stop it doing that? So we'll start with another variant of the picture before that I had before, which is QEMU. We've got the libxen foreign memory library there instead. We've got privcommand again, and we're going to libxen foreign memory is going to issue an nmap IOREQ tool, to map domain B's memory. But there's nothing to stop the compromised QEMU. First of all, I say guess domain A is compromised QEMU, but it's going to issue the IOREQ for domain B. So A should not be able to do that, but there's nothing to audit the target domain. So now we've mapped domain B's memory, and A can read it, essentially using the compromised QEMU. So what are we going to do to stop that? Well, we have a new IOREQ priv command called restrict. And what restrict does is it essentially says that we run this IOREQ before the domain A starts operation, so before there's any possibility of QEMU being compromised. We tell libxentoolcore foreign memory for the handle it's got open that it's only allowed to do operations for domain A. And that means that when domain A then successfully compromises the QEMU, it tries to issue an nmap IOREQ for domain B's memory, and it's refused by Xen because Xen already knows that priv command refuses it because it already knows that handle cannot be used for mapping domain B's memory. It's restricted to domain A. But there's a slight problem with restricting memory handles in QEMU, and that's there's a lot of them. So when QEMU opens as an API, that you can see there's like foreign memory, device model, store, event chain, printer. All these things are separate memory handles. Some of them, like the two on the left, go to priv command. Some have their own dedicated drivers, like Xenbus, event chain, embed. But QEMU has a lot of handles, and how do we go about restricting them all? It would be a lot of code change to just do that on an ad hoc basis. So there's a new library, which essentially is one to rule them all. It's called libxentoolcore, and that is there, I think, in 4.11. Not sure whether it went in before. Yeah, it's pretty new. And so the idea is that sits there, and each of the other libraries registers any handle that's got open with toolcore, and it uses a new API for that. XenServer register active handle. So every interface will now register an active handle with the toolcore library. And that means that then QEMU can issue a restrict all operation to toolcore. Toolcore knows about all the active handles that QEMU's got open, and it calls a restrict callback. And for libxentoolcore foreign memory, that will then cause the IOREQ priv command restrict operation to be issued, restricting that file handle. Some of the libraries don't actually have any mechanism to restrict so far. So there's a default way of restricting, which is slightly hacky, but it works, which is basically where we take the open file handle and we dupe it onto a file handle opened against dev null, which means that basically anything that's issued down that file handle from then on will go nowhere. But the problem is that QEMU still runs as root. Well, actually, I think I should mention also that when the toolcore restrict operation runs on libxen device model, it also issues a restrict. And that's the way in which we stop, when the restrict operation is issued, it means that basically no file handle can be used to compromise QEMU. No open file handle can be used by the compromised QEMU to then attack Xen using the arbitrary hypercall interface, because we closed that operation off in privcmd at the point where we restrict it. So any restrict operations issued down a file handle to privcmd will cause privcmd to then refuse any arbitrary hypercalls from that point onwards. But there is a problem, which is that QEMU still runs as root. So there's nothing to stop QEMU just opening a new file handle against privcmd and then using that to issue unrestricted hypercalls. So how are we going to stop QEMU running as root? Well, sorry, how are we going to stop this job? Let's not run QEMU as root. Let's try and run it as something else. QEMU already has an option to run as an alternative user after the initial setup, and that's the run as operation. But that is actually not a UID, that's a user account name. But let's try setting up user account name to run QEMU as, and let's just run it as that. So we have now QEMU, the three QEMUs running with our new user account. Obviously they're all sharing the same UID because the user account only has one UID. But why isn't this a good idea? Well, if one of those processes gets compromised, then it can then issue a ptrace against one of the other processes for the same user. And now whilst QEMU can't directly see the guest's memory because of the other restrictions we put in place. It can still see the interactions now between that QEMU and its guest, so it can still introspect on it. So what are we going to do about that? Well, the best thing to do will be to run your QEMU as a separate user ID for each instance. And we can do this, well, because DOM ID space is 16 bits wide, or actually it's slightly less than 16 bits wide, because there's some reserved DOM IDs at the top end. I think it's 15 bits. Actually not. I think it's 0, well, my research says 0, the DOM IDs from 0 through 32,751 are valid DOM IDs to use, and everything above that is not. Happily, on most OSs, including Linux, the UID space is 32 bits wide, so it's significantly larger, which means we can choose a window in that UID space to map the DOM IDs onto. So we can then have a one-to-one correspondence between a DOM ID and a particular UID, just using the base value, which is convenient because otherwise we'd have to tell the tool stack how to map every single DOM ID to a UID. So we still have an issue.
What was the UID max?
The DOM ID max is 32,751, which equates to 7 FEF. So 7 F.
I made a note of a document that's
7 FF0, yeah, basically from onwards is the special UI, special DOM IDs. So we still have the issue that the run as takes a user account, so we potentially have to set up a user account for every single one of our UIDs, which is slightly awkward. But happily that's been solved. Ian Jackson upstream patched a QEMU not long ago where we can actually use a UID-GID pair instead of a username, and that means we can now run QEMU directly as a UID rather than having to set up a user account for each individual one. But say we're now running QEMU as a separate UID, since we've got base plus 1, 2, 3, so on, all up to that DOM ID first reserved value, as I mentioned before, which is 7FF0 minus 1, so that's the 7 where the 7FEF comes from. But as we start and stop guests, we're going to be starting and stopping QEMU processes, and there's a problem with this. Because the DOM ID is eventually going to cycle back round. Obviously it's not going to cycle back round to 0, because that's DOM 0. So we're going to cycle back round to say DOM ID 1, and we're going to come back round again. But there's going to be an issue at some point, potentially, which is that there's something lurking behind that one, and that something is a compromised QEMU process that didn't die. Now, why didn't it die? Well, it turns out that killing processes is a bit tricky. If your compromised QEMU starts executing that loop there, which is a type fork loop, then it's going to be changing process ID so rapidly that the tool stack trying to kill it by process ID is not going to win. Even if you try kill all, it's not going to be able to, certainly killing it by the original PID that it was spawned with is not going to work, but even if you use a kill all to try and follow it, you're not going to win the race. That QEMU potentially is going to stick around. And obviously, as we said before, with a shared UID, that means potentially it can also introspect on the new DOM ID that spawns a QEMU with the same UID. So there turns out to be a way to fix this, which I think George put together a blog about. And this is using a special PID of -1 passed to the kill operation, which says to Linux, or I think it's actually public standard, it says kill everything in the same UID as myself, as me, except me. And that allows you to then kill QEMU by changing to its UID and then issuing the kill operation. But we have to be slightly careful, because if we were to blindly change to the same UID as QEMU, then there would be nothing to stop QEMU killing the tool stack. So we have to use a specially crafted set-res UID call, which allows the tool stack to change to be the same UID, or the particular tool stack process to be the same UID as QEMU, and kill it without being killable itself. Because it turns out that the UIDs that can be killed and the UIDs who can kill are slightly different. There's 3 different user IDs in Linux.
So is tool stack also a different process?
Well, you could have the tool stack spawn a different process for this purpose. The tool stack can have as many processes as it likes. So the way in which you do this is you probably spawn a kill process, which then changes to be the UID of the QEMU wants to kill, and then does the kill operation and finishes.
And that guy has to be the part of the group that you created earlier, right?
You change the BB. Wait, go on, George.
Well, I was going to say, the kill -1, it says kill everything I'm allowed to kill.
Right.
Not kill everything of my user ID.
Okay, all right.
So you have to set it up such that you are allowed to kill them, but they're not allowed to kill
Yes,
you,
that's-
and it's very
that's it,
tricky. So
Yes, but as I say, there's 3 different user IDs. There's like real, effective, and safe. And basically, if you change the right ones, then you can kill something else, but it can't kill you. So that's the way in which we would have to do the kill. And as I say, George put something together. Actually, there's a GitHub repo there where he's got some code you can go look at if you want to. So to summarize, we've got direct resource mapping to make this attack on QEMU more difficult in the first place, but if QEMU does get compromised, we've got auditing and restriction on the interfaces that QEMU can use to try and make the attack less likely or to try and limit the QEMU's ability to attack other guests or Xen itself. And we've got QEMU deprivileging to stop it bypassing those restrictions and opening the arbitrary hypercall interface again. Sorry, Karen.
Can you show George's URL again?
Sure.
Just to see what's in there.
Runner.
Okay.
That's a
Right, so a couple of problems remaining. Migration and PCI pass-through. Now, when we do QEMU deprivileging, there's a problem with migration, and that is that the signaling, the traditional way in which migration sending and receiving has been signaled is done using XenStore, and that's one of those handles that we restricted. There is no deprivileged interface to XenStore. You have to be running as root, so that handle actually gets closed off, which means if you try to migrate, you can no longer talk to XenStore, and it's not going to work. Now, the way around this is that QEMU has a signaling mechanism called QMP. This is the way in which QEMU is supposed to be driven. The XenStore interface is kind of a legacy, slightly hacky way of doing things, and I think Anthony has actually upstream patches by now. He certainly had candidate patches which swap over from doing the signaling via XenStore to doing the signaling via QMP, so we can solve that problem in that fashion. There's still a question of auditing here, which is we want to be sure the various QEMU handles are restricted before we expose it to any untrusted input, and inbound migration is untrusted because the source domain could have been compromised, and then when we read the save record back, we're potentially reading untrusted data. So we also want to audit the inbound migration stream before we trust it. We want to restrict QEMU before we read the inbound migration stream, because otherwise that inbound migration stream could compromise QEMU before we manage to do the restrictions. The Injection's written a tool to do the auditing. It's fairly straightforward to run. You just need to start the guest pause, run the tool, and it will tell you, it will give QEMU a clean bill of health to make sure that it's adequately restricted before you start reading the migration stream. Second problem is PCI pass-through. It's using potentially interfaces which require root privilege, and that's a slightly tricky one. I think there's a session later on, or a design session going on during the summit about running PCI pass-through with restricted QEMU. But at the moment, basically, your only option is continue to run QEMU as root. So further work we might do on this. These haven't been implemented yet, but these suggested future things we should do is run QEMU in Chirrut. Even if it's deprivileged at the moment, QEMU is still running with visibility of the entire file system, so any world readable, writable handles it can still get access to. Running in a Chirrut would close off some of the attacks it could mount using that. Next one is, we can do that using a command line option that already exists in QEMU. But the problem is with that, virtual CD-ROMs currently generally rely on having QEMU open ISO files. and that could limit your ability to open ISO files because you have to somehow get them into the chroot. There's a way of doing that, which is the QMP has an addfd command, so you can actually have the tool stack open the ISO in the first place and then pass the active FD into QEMU. That would work around that issue. Next thing we should do is set the R limits, because say R limit core is set to unlimited, and then the compromised QEMU crashes, it could then start to fill DOM0's file system with core dumps. RLIM F size worth setting again, because of compromised QEMU, you could just start to write a file and just fill up DOM0's file system and DOS it that way. Next one is Linux namespaces, because again, compromised QEMU has full visibility of the network namespace and the IPC namespace, so it could potentially try to mount attacks even if it's deprivileged using those. And that's something that we can do using the unshare command.
So, of those three, I think you really should add in there that addfd. We should really do seccomp and aim to not have QEMU open files itself. And toolstack should really pass file descriptors in and just block off QEMU from ever opening a file. I mean, we're going to take off so many XSAs off the table that we've had.
Well, potentially, yeah, but obviously if you have a chroot, you could potentially restrict the ability for QEMU to open files by just not giving it visibility of anything that's interesting.
It's worth saying that all of this stuff is things we've hacked into XenServer.
Well, I don't know where we are with the chroot, whether we've got that implemented. Yeah, we do.
But I mean, why chroot? Why not just take the open syscall out of QEMU entirely, and let's just give it all file descriptors and things.
QEMU upstream has already seccomp support.
Yeah, no, it does. And libvirt has used it for years, and so. Of course, sure. But I'm saying let's not take a small step. Let's just take the big step, and that's.
Yeah, well, it's an option.
And I mean, obviously, sit down and write the code. I get it. I mean, I'm not the first one to reply to that on the mailing list, but yeah, I mean, I think that should be a meaningful goal rather than trying to see it, because the CH root is really a small step. I mean, you can break out of the CH root. You can do.
Yeah.
And so I mean, potentially also with your kill, why don't we look at like unsharing into a PID namespace?
Yes, the other thing is that all of this is fine on Linux and less of it's fine on the BSD. Whereas things.
I mean, so yeah, I mean, certain amount of stuff you can't get into QEMU upstream on the basis that it's supposed to be portable. So yeah, there's issues there. George has.
Yeah, I was just going to say, I'm definitely in favor of doing everything we can. So seccomp, namespaces, whatever. We do also want this to work on FreeBSD,
Of course.
which doesn't have seccomp or things like that. So I think we just toss as much stuff as we can.
I mean, there is similar support in BSDs. They just as seccomp and all that. I mean, libvirt on BSD uses that. So that's what I'm saying. Like, I'm not trying to be a thing, but it's of course it's going to limit us like a DOM0, like an RTOS DOM0 is not going to have all that. But I mean, let's rather than trying to target the simplest compromise, let's try to use the best available for each group.
Well, I think we want to be able to do all of them, and then choose whatever's available.
Sure.
Essentially, so that the tool stack tries to run QEMU in the most secure way it can on that particular system. Right. Any other questions? Right, I don't think so. So I guess I'm done.